Hello, I'm going to start off this video uh, with the continuation to the previous one where I had ended the video with a question that is we wish to obtain the magnetic field intensity at the point O, which is lying at the center of two squares, two incomplete squares, because one of them is having a side of 2 centimeters each, but we can see only a quarter of that, which is exactly over here that you can see. And the other one, the bigger sphere or bigger square of each side of length 4 centimeters, which is which is 3/4 of the entire square. Now, going back to the formula that we had obtained for these quarter terms over there in the denominator, in the bottom of the page, not the denominator. In the bottom of the page, you can see that we have obtained this expression over here, and this is for a quarter of the square. That is 1 over root 2 times of mu naught I over pi r, r being the distance in that case. Well, that's not r, but that's a actually. So in that case, we'll be using that formula over here to obtain the final expression of the magnetic field that we wish to obtain at that point. Now, as you can see, the bigger square, that's 3/4 of that quadrant. So 3/4 of that means 3 over 4 times of 1 over root 2 times of mu naught I over uh, pi times of a. A in this case is 4 centimeters, so I'm just using the term 4 over here. We'll take care of the centimeters later. And then you also have 1/4, the quarter of the small square. So for that we have 1 over root 2, that the formula that we have obtained, mu naught I over pi times of 2. That will be in centimeters as well. So now we'll take care of the formulas that we'll take care of the centimeters and the scales of measurement having obtained. Now, in each of those cases that you can see over there is that the direction is counterclockwise. Now, in case of counterclockwise direction, uh, the net field for both those segments will be out of the plane, which is denoted by dot encircled. So this is out of the plane. So considering that, we'll be obtaining the result over here. So the result here is equal to, well, that is 1 over root 2, that can be taken as the common term. 1 over root 2 is common. What else is there? Mu naught I, that is a common term. We'll put the values later. Over pi, that's also a common term. And instead of 4 in the first case, we take away the 2 out of it, and then the 2 also goes out for the second term. So now what's left in the bracket? Well, in the bracket we have 3 over 4, that's there for the first term, and then we have 1 over 2. Now 2, as you know, the 4 and the 2's, they are in centimeters. So we'll be having a common term, that is 10 raised to the power 2. We'll keep that outside bracket. 10 raised to the power minus 2 in the denominator goes up to 10 raised to the power plus 2. So we'll take that out of the bracket. Now this entire thing has been taken as common, so we'll keep the 1 over there. And then we have 10 raised to the power 2 for the centimeter, which was divided in the denominator, and then we took it up to make it 10 raised to the power plus 2. Now we calculate this value. If the value of current has it been provided, well, I don't think the value of current has been provided over here, but well, let's take it some value just for the sake of calculation. We have gone this far. So for the sake of calculation, I take the value of current as supposedly 1 ampere. So if the current over here is 1 ampere, it's moving in the counterclockwise sense, so the direction has been taken care of in this case. So we have 1 over root 2, and mu naught over pi is simply 4 times of 10 raised to the power minus 7, and then you have the current, which is the unit value. Then we have the 2 over here, and 10 raised to the power 2 is also there, the common term. Then this is 3 over 8 plus 1, which makes it 11 over 8. That's more or less the case that we were supposed to obtain. You can just simplify this. So the 4 cancels out with the 8 over there, so you have left 2, and then you have 4 root 2 in the denominator, and 11 over there. So 11 times of 10 raised to the power minus 5 over 4 root 2. You can simplify it further by taking the values of all of these things, and this will be in Tesla. That's the value of the magnetic field at that point. So that's more or less the case that we were supposed to obtain as per the question. Well, the current wasn't provided, but now it's been given and the value has been obtained, and the direction also has been obtained because it's a vector quantity. All those arrows being well, they're not in the counterclockwise sense, sorry, I beg your pardon. This is in the clockwise sense. It's my bad. It will be into the plane. It'll be into the plane because it's in clockwise sense, so it's going to be directed into the plane. Now again, in another condition that we are going to use this time for a circular loop. Now in case of circular loops, what we know is that at the center of the circular loop uh, of a certain radius, let us say this is A, and let's take the current to be flowing in the clockwise sense. What we know of is that from our discussion for magnetic field intensity at the center of a circular current carrying coil, let the current be equal to I in this case, flowing in the clockwise sense, then the magnetic field intensity at the center will be equal to mu naught I over 2 times of A being the radius in this case, and because it's in the clockwise sense, it's going to go into the plane. So it's going to be directed into the plane. Now, for n number of such turns, n number of such turns, what we know is that because the magnetic field for each of those turns is going to be directed along the same direction, so even when we add vectorially, the net magnetic field in this case is going to be n times of the magnetic field due to a single turn, which we have already obtained to be equal to mu naught I over 2a. So this is simply mu naught n times of I over 2a, because it's n times of b. It's uh, it's uh, the usual way of writing that n between mu and I, so that's why I've written it over there, but we can put that n before the expression as well, like in this case that I've done. Now if we are to consider a certain sector of that circle, and we have the current flowing in that sector, that it's actually the arc of that circle, and this what I have constructed is a sector which is subtending an angle theta to the center. Now in this case, with the radius again taken as a, we have a small portion of that circle available, for which we will be obtaining the magnetic field at this point. Now the magnetic field in this case is going to be equal to mu naught I times of 2a, that is for the entire circle, but that's not the case over here. So this is out of that entire circle taken in 2 pi radians, we have a theta radian available if it is taken in radians. But if it is in degrees, then we would rather consider the magnitude over here only. So if it is in degrees, then the expression will just goes to 360 degrees, out theta out of 360 degrees. This is in degrees if it is in degrees, and this in radians. Now let's use this to obtain the expression for the magnetic field, or rather calculate the magnetic field for given parameters in the next figure that I'm going to draw. Now suppose we are given the case over here that a current carrying arc, a current carrying wire in the form of two arcs that it has made as it has moved from the point A to the point B, and then from B over to C, and then back to D, and then somewhere it continues somewhere in the circuit. What we wish to determine is the magnetic field intensity at a point O, which is lying as shown in the figure. Now, as you can see that O is actually the center of a sector of which the two arcs form a part. The the straight line, the straight wire, the straight segment of the wire that is B to C, that does not contribute to the magnetic field because the point O lies along its line. So if any point is lying along the line of a wire, such as that point, then here you won't be getting the magnetic field due to this current carrying element as per Biot-Savart's law, because the angle in that case will be 0, so sine of 0 is going to be 0. So now what we can consider is that the magnetic field is absent for that segment, but however we have two segments, and in both those segments, that is both those arcs from A to B and then from C to D, we have the current flowing in opposite directions. So the magnetic field will be in opposite directions as well at the point B. So as you can see, from A to B, it's in the clockwise sense, so the magnetic field is going to be into the plane in that case. So that magnetic field which we wish to determine at the point O, which now lies at a distance of 4 centimeters from that arc, subtending an angle of 60 degrees to it. We have the formula just as above, that is mu naught times of the current here given is 10 amperes over 2 times of the distance is 4 centimeters, so 4 times of 10 raised to the power minus 2 in meters, and the angle as you can see is in degrees, so it is 60 over 360, and that's the case for the magnetic field intensity due to the element AB, but it's directed into the plane. What about the case of magnetic field due to CD? Well, because of CD, we have the equation as mu naught times of 10 over 2 times of, now the distance over here, as you can see, the gap between those arcs is 1 centimeter, so 4 plus 1 makes 5, so 5 times of 10 raised to the power minus 2, and that again is 60 over 360. So the angles remain the same, but this one's going to go outside the plane now because of the anti-clockwise sense. Now in both those cases, if you observe that the value of the magnetic field due to the element AB, because it's nearer, it will have a greater impact, and obviously the magnitude is going to be greater. So eventually, with two opposite vectors BAB and BCD, we have the direction of the resultant to be along the greater one. So in this case we'll be having BAB minus BCD as the resultant B vector that was to be determined. That means that the final magnetic field is going to go into the plane. So having known the direction, now we just need to obtain the value, the magnitude, that is. So the magnitude of B in this case is going to be, well, all the terms are going to be taken common, so we have 4 pi times of 10 raised to the power minus 7 for mu naught. Then we have the 10 ampere as the common term, and then we have 2, and then we have 1 over 6, which comes from 60 over 360, and then finally 10 raised to the power minus 2, also the common term, and we have 1 over 4 minus 1 over 5, and from that you can calculate the value. It's pretty straightforward. It's going to be 1 over 20. Now this is 4, 10 is 42, and this is 20, so all of them can get cancelled out. And what you have left is pi over 6 times of 10 raised to the power minus 5 Tesla. And that's going to be directed into the plane, considering the case of magnetic field being a vector quantity. So that's more or less the approach to all these kind of numericals. We'll get into more such numericals in the N.E.E.T corner. Till then, thank you for watching.